Okay, so this is the question 2 on the final, where we had the cue ball hitting the 2 ball, the 2 ball hit the 3 and the 4 ball. All of those balls, same mass, and this is just a picture of playing pool. Of course, you have 15 similar billiard balls lined up, and so the best break, proved by physics here, is just if you're able as a pool player to just hit the 1 ball. In this case, it's the 2 ball. The cue ball is, the 1 ball. So if the 1 ball could hit the 2 ball square, just right in the sweet spot, head on, we have the greatest distribution of all of the other billiard balls around the pool table. So it makes it for easier shots from the pool players, and you even have a great chance of a couple of them going into like the back pockets or even side pockets on the pool table. So anyway, when the first ball hits the second ball, by conservation of momentum, the first ball stops, V1 final is equal to 0. That same speed that it had initially, V1 initial, carries on into V2 final. So it's a straight conservation because the masses are the same, so the speeds are the same. And of course, momentum is safe everywhere. So as the 2 ball hits the 3 and the 4, they go off at a glancing angle theta and phi, respectively. So V3 final goes off at angle theta, V4 final angle phi, and ball 2 continues straight ahead. So this is this picture here. Now I'm saying, in class that if you hit it head on, there's a great chance that the balls at the edges will go into their, back pockets. If you watch how, the pool balls are set up on the pool table, you do have a great chance for that happening should you hit ball 2 head on. So anyway, we can translate this picture accurately geometrically by translating this vector V4 final to the tip of V3 final, tip to tail method back in chapter 3 for adding vectors geometrically. And so we have this right triangle situation, very similar to the example problem 9.9. V2 final is here, the hypotenuse. V3 final is one of the legs, and V4 final is the other leg of the triangle with their respective angles theta and phi. Step 1, we look at momentum in the x direction. We know momentum is saved everywhere, so we're just going to get the equations of the momentum in both x and y directions. In this case, V1 initial, its momentum is the same as the momentum on the right side here, the final side, which is V3F cosine theta, V4 final cosine phi, plus V2 final, all in the x direction. Initial equals final in x. And the same thing goes for y, nothing initially in y, and then it gets split up into V3F sine theta minus V4 final sine phi. And here is negative V4 final sine phi. It's negative because it points down. V3 final sine theta points up. So, right, so just labeling that again, at least for the first time on both sides. Right, so we have V3 final sine theta, and this is negative V4 final sine phi. Okay. At some point in physics, any physics problem, you just want to label everything that you see about it. You write all of the stuff that you know about it mathematically. It's a right triangle, so okay, here's a Pythagorean theorem, hypotenuse squared, c squared equals a squared plus b squared, v2 final squared equals v3 final squared plus v4 final squared, just to have something for accounting. We may need it. Right, it turns out we do. So step 3 here, the problem asks us, well, I'm asking you to find V3 final and V4 final. So I was setting out to find expressions for V4 final. So I know that V4 is comprised of its components with respect to the angle phi, cosine phi, V4 final cosine phi, get an expression for that, get an expression for V4 final sine phi, and that's easy. We get that from step 2. And this is from step 1, V4 final cosine phi, right here. So then, in my pursuit of finding V4 final sine phi, or V4 final, I could put both of those components into Pythagorean theorem, and then I could square everything, all of the parts of V4, and it would turn out that you get a similar expression for V3, but I haven't done that option, but it turns out that you might get to the same conclusion as the other option that I did choose, where you come back to the same thing. You haven't really shown what V3 and V4 final actually are, but you can try it. So what I did, something simpler, use the Pythagorean theorem here, get an expression for V4 and also for V3. So I'm going to see if I could transpose or do something with both in order to find out what I need to find out, the values of V3 and V4. So like if you did it one at a time, you're going to come back to step 4. So that's not a good thing. So what you can do is take an expression for V4 and for V3 simultaneously and see what you can see. And again, that's intuition playing into the math. Because as I said in class, as I've been saying, physics is a combination of intuition, concept, and math. And you're just always juggling, you're always trying your best to keep that as focused as possible. My intuition from the concept, and even before concept, intuition to concept to math. And usually, a lot of times, that's straightforward. Some other times we have to think of a couple of options, just like we're doing here. So, okay, V4 final squared equals V2 final squared minus V3 final squared. I get an expression for V4 final and then V3 at the same time, simultaneously substitute them here, and I get this expression. Okay, I square both sides, don't like radicals. Get rid of the V2 finals. I have negative V3F squared, sine squared phi, negative V4 final squared, sine squared theta. And the negatives go away, both sides, and I get this expression here. Take the square root of both sides, and I get V3 final sine phi equals V4 final sine theta. Well, that's the transposition of the original equation, which is V4 final sine phi equals V3 final sine theta. So that tells you, shows you that V3 final is equal to V4 final, which should make some intuitive sense since both of the balls, all of them, especially those two at the angle, they're going to go off at the same speed because they have the same mass. And it's also such that they're going to have the same speed along their hypotenuse, their respective hypotenuses, meaning this direction for V3 final, V4 final here, they have to have the same, it must be the same such that the momentum is saved everywhere else. And that's a slight proof you can travel down if you want, but it all shows itself out here in the math. V3 final is equal to V4 final. So it could be ones, whatever, it's the same number. So that means that this triangle is a 45, 45, 90 triangle where the sides are 1, 1, and the hypotenuse is radical 2. Angles are 45, that's one of the questions. And V2 final is faster than V3 final, which is equal to V4 final. It's actually 71% faster. So we answered everything. V2 final, 71% faster. Angles are the same. And they will pretty much always be complementary. So because like we see in the example 9.9, how they give you an angle 37, well, it should not surprise you that the complement, that the angle, the other angle is 53. So yeah, that's the logic I want you to use and take off so that you could get this relationship. Okay, guys, take care. Have a great break. God bless you guys. And talk to you January 7th.